Welcome to The Explainer. Today, we're diving into one of the most critical topics in Kubernetes, how to make sure your data doesn't just disappear. Let's start with a problem that is basically a nightmare scenario for any developer. You've built a stateful application. A pod restarts, maybe it crashed, maybe the node got updated, and just like that, poof, all the data that was just there is gone. So why does this happen? Well, by default, a pod's storage is ephemeral. That's just a fancy way of saying its lifespan is tied directly to that single container instance. When the container goes away, so does its storage. Now, that's fine for something like a temporary cache, but for a database, that's a total deal breaker. You absolutely need that data to stick around. So in this explainer, we're going to break down exactly how Kubernetes solves this whole mess. We'll start with the really clever abstraction at the center of it all, we'll follow the lifecycle of a piece of storage from start to finish, and then we'll see how you can pull it all together for those really complex, stateful applications.
Okay, let's get into it. The whole Kubernetes solution is built on this really brilliant idea, the separation of concerns. It creates a clean line between the folks managing the infrastructure and the folks building the apps that run on it.
On one side of that line, you have the persistent volume, or PV. The easiest way to think about this is as the supply. It's a real piece of storage, like an AWS disk or an NFS share, that an admin has made available for the cluster to use. And on the other side, you've got the persistent volume claim, or PVC. And if the PV is the supply, well, the PVC is the demand. It's how a developer says, hey, I need some storage, without having to know or, frankly, care about the nitty-gritty details of where that storage actually comes from. And this right here really lays out that separation perfectly. Admins manage the infrastructure, and they supply storage using PVs. Developers manage their applications, and they demand storage using PVCs. It creates this beautiful, clean contract between those two worlds. So, how do these two things, the PV and the PVC, actually connect and work together? It's not just a simple link, it's a really well-defined lifecycle. So let's just walk through the four main phases that every single volume goes through. Every persistent volume in Kubernetes, without exception, goes through these four steps. First, it's provisioned. Then, it gets bound to a claim. Next, it's used by a pod. And finally, when it's all done, it's reclaimed. Now, that first step, provisioning, can happen in a couple of ways. It can be static, where an admin just creates a bunch of volumes ahead of time, kind of hoping they've guessed right about what people will need. Or, and this is way more common, it's dynamic, where volumes get created automatically the instant a developer makes a claim. So once a claim finds a matching PV, or one gets dynamically created for it, the Kubernetes control plane binds them together. And this is a totally exclusive one-to-one lock. That piece of storage is now reserved, it's off limits to anyone else. Now, while that volume is being used, Kubernetes has this absolutely critical safeguard in place. It's called Storage Object in Use Protection. Basically, it means if you try to delete a PVC that a running pod is still writing to, Kubernetes will just say, nope, and stop you. It prevents you from accidentally pulling the rug out from under your own application. And what happens at the very end when you delete the claim? That's where the reclaim policy on the persistent volume kicks in. Retain is your safety net. It keeps the volume and the data around for you to recover manually. Delete, on the other hand, just cleans everything up, which is great for keeping costs down, but you have to remember, that data is gone forever. Okay, so we have this great system for asking for and getting storage. But as you know, not all storage is the same. Sometimes you need a disk that can only be attached to one machine at a time, and other times you need storage that can be shared by dozens. Well, Kubernetes gives you some really powerful ways to define and automate exactly what you need. These are called access modes. ReadWriteOnce, or RWO, is probably the most common. It means the volume can only be mounted by a single node at a time, perfect for a database. But then you have ReadWriteMany, or RWX. That's for shared file systems like NFS, where you need a bunch of pods on different nodes to all be reading and writing to the same place at once. And the real engine behind all this automation is the storage class. You can think of it as a blueprint or a recipe that tells Kubernetes how to create new volumes when somebody asks for one. An admin can set up different classes, like maybe a fast SSD class for production databases and a cheap archive class for backups. And this is where it all comes together so beautifully. Look at this flow. A developer just creates a PVC and says, I want the fast SSD class. And that's it. The system takes over, calls out to the cloud provider to spin up a new disk, creates the PV, and binds it, all without a single bit of manual work. It's amazing. But there is a little trap here. What if the storage gets created in, say, availability zone A, but then your pod gets scheduled to run in availability zone B? They can't connect. That's where this key setting, wait for first consumer, becomes a lifesaver. It tells Kubernetes, hey, hold on. Don't create the storage until you know exactly which node and which zone the pod is going to run in. It guarantees they always end up in the same place. So we have all these fantastic building blocks now, PVs, PVCs, storage classes. But how do we actually put them together to run something really complex, like a distributed database cluster? Well, that is where the stateful set comes in. You see, a regular deployment treats its pods like cattle. They're all identical and disposable. But a stateful set treats its pods like pets. Each one gets a unique stable identity that sticks with it, even if it gets restarted. And that is absolutely essential for running stateful systems. This stable identity has a few superpowers. First, you get stable networking with predictable names like DB-0, DB-1, and so on. Second, you get stable storage. The stateful set uses a template to automatically create a unique, dedicated volume for every single replica. And third, you get ordered operations, so you can make sure your database primary starts up before any of its replicas try to connect to it. And this is the real magic right here. When a pod managed by a stateful set fails, let's say DB0 goes down, its replacement is guaranteed to also be named DB0. And because it has that same stable name, it automatically finds and reattaches to its original dedicated persistent volume. The state is just preserved perfectly. And this brings our whole story full circle. Just imagine, a database pod, PG-DB0, is running on a node, and that node suddenly crashes. Kubernetes sees this and schedules a new pod, also called PG-DB0, on a healthy node. That new pod automatically reattaches to its existing volume claim. The database starts up, finds all its data exactly where it left it, and just resumes service. Zero data loss. By abstracting storage away from the underlying infrastructure and giving us powerful tools like StatefulSets, Kubernetes really transforms itself. It goes from being just a runner for stateless apps to being a true operating system for the cloud, ready to handle your most critical, most important workloads. So the only question left is, what are you going to build with it?